All right, so today we're going to talk about impulse, which we did do freshman year, and Mrs. Leas did with you freshman year. So we're going to talk about a collision, and then we're going to discuss the change in momentum for each individual object, which is how we're going to get to impulse. So I'm going to consider two particle-like objects. And that just means that they're pretty symmetric. I don't have to worry about them. I don't have to worry about like one side being affected differently than the other. It's just, think of them as marbles of different masses. Colliding or striking. So I'm going to have my object on the right, and I'm going to have my object on the left. All right, so because these objects are colliding and coming in contact, they are exerting forces on each other. What can you tell me about those forces? And yes, they will be a third law pair. So the one on the left exerts a force on the one on the right, and that isn't going to be a constant force. It's actually going to vary, and I'll show you how it varies in a minute. And then the object on the right exerts a force that is equal in magnitude but opposite in direction on the object to the left. And I suppose that the strength of these forces could be constant, but chances are they're not, because if you think about it, especially if one of those objects is a little softer, okay, that object is going to deform a little bit. You kind of get like that dimple in the ball when you push two balls together. Okay, so that force isn't going to be constant because just the interactions between the balls or between the objects is going to change as they impact. So my force as a function of time might kind of sort of look something like this. That's not necessarily symmetrical either. And this is going to be my f of t. And that force is going to be applied while the objects are in contact between some t1 and some t2. And of course, I'm going to say that I'm going to call the difference between those times delta t. Wait a minute. Don't get all mathy on me. think I was okay the way I was before. Very much, actually. Because I think we write f of x versus x all the time, and then the curve that we draw is in fact f of x. I think I have seen axes labeled that way. But if it makes you happier to have it be f, I don't really care. It's not important. All right? That's what the graph looks like. Okay. We're not nitpicking today. All right. Okay. All right. So if I took the time to write down forces, what's the thing I'm going to do next? This is kind of my free body diagram. F net equals ma. Okay? So F net equals ma is the way I write what? What is that? Newton's second law. But we learned the other day that there's another way to write Newton's second law. You can look in your notes. It's okay. That's why you took them. Yeah. That my F net is also equal to, effectively, the change in momentum. So I'm going to apply Newton's second law to my object R. It doesn't really matter which object I apply it to, but for object R, the force is in the positive direction, so it just makes my life easier. Okay? And I'm going to rewrite Newton's second law so that it says dP is going to be f of t dt. Because in the x direction, in that horizontal direction, the only force that I really have is my f of t, my force from the other ball. And while you're not quite there yet, in another couple of weeks, you're going to see an equation like that, and you're just going to have to integrate it. You're not going to be able to stop yourselves because it just screams to be integrated. So we're going to integrate both sides. And we're going to integrate p, we're going to make definite integrals like we did in calculus, from some initial value p to some final value of p, whatever it is. Because what am I going to get when I integrate dp? P, right? Just like when I integrate x dx, I get x. Okay. And then on the other side, I'm going to have my integral of whatever that force is times dt, and I'm going to integrate it from, what did I call it? T1 or T? Ti, T1 and T2. Okay, but you know what? We're going to change them to Ti and Tf. So actually go back over here, and we're going to call that Ti and Tf, okay? So go back to your erroneous graph, your graph of questionable provenance, and make it Ti to Tf. Okay? Just so that I have all i's and f's instead of a mix of i's and f's and 1's and 2's. Okay? And then my integral looks like that. Maddie. Yeah. Because remember, like what we said in calc the other day, I can take the integral over anything. It's just that the d blah tells me what I'm integrating over. Yes, it would be a little imaginary one there in front of the dp. But I find that when I put that there in calculus, people get freaked out. So I don't put it there. Okay. You know how to do this. The letters have changed, but you know how to do this. This should not look horribly unfamiliar. Okay, so like we said, the antiderivative of dp will be p, and just like we were talking about in calc, I'm going to evaluate that between my limits. I'm going to leave the other side the way it is because I really don't know what f of t is. And then I'm going to substitute my limits in here. Those should have vectors on them. So I get pf minus pi is my integral from ti to tf of f of t dt. This is what? What can I always call an integral? Not antiderivative in this case. What? I don't know. It's the area under the curve. And that's appropriate this time because I have a curve. And I call this, which I could call delta p, because it's the change in p, the standard nomenclature that we use for that. But I also call it j, where j is impulse. And each of the objects in my collision have their own impulse. So since we are talking about, we wrote Newton's second law for my object R, that tells me that JR is equal to the integral from TI to TF of f of t dt. Because that's what I figured out. That's what I was doing all of this calculating for. It was just that big object on the right. It's what I named the object on the right. The other object is L for left. So, what do you think JL is going to be equal to for the object on the left? Well, yeah, the same thing. FT is going to be negative, right? Because it points in the opposite direction. The force does. All right, and these are all vectors. Notice they all have vector symbols. So this is going to be negative the integral from TI to TF f of t dt, because remember from the properties of definite integrals that we talked about earlier this week, if I have a constant like a -1, I can just pull that out of my integral. Which also means that JL is going to be the negative of JR. So remember, R and L are my two objects that are colliding, and so their impulses are going to be the negative of each other. Okay, makes sense? With me? All right, so of course we have kind of a, I wouldn't call it a pointless theorem, but we have the impulse, it is linear. linear momentum theorem. Which says that P final minus P initial, which is equal to delta P, is equal to the impulse. Kind of an obvious statement based on what we just talked about. Like the letter, the symbol. Oh, wow. Unless you're supposed to be calculating it yourself. Just saying. One more way in which you'll be unprepared when the machines take over and then they break. Just saying. You're pretty good up to 10 because you got fingers, but... Next. So if the impulse J is equal to the area under the f of t curve, then I can figure out that area any way I want. And based on what we've been doing in calculus this week, I can figure it out a whole bunch of different ways. I can figure out the area like we talked about today by finding the antiderivative and evaluating it at the upper and lower limits. How else can I figure it out? Calculator. And then what else can I do? Yeah, I could look at the actual shape and try to get the geometry from it. Well, if you remember that curve that I drew a couple slides back, that kind of looked something like this. Okay, again, not symmetric. And here was my TI, and here was my TF. Okay, I don't know what that's going to be. All right, that's kind of a weird area. It's not, and I really sincerely mean this, it's really not a parabola. You might get lucky that it's a straight line or something you can figure out. But I don't know what that is. However, if you recall, which again we did in calculus today, how to find the average of f. How did we find the average of f? This can be f of x dx. I could make it f of t dt, but I can use x here. Okay. So in physics, just because that's the way we do it, I write f average a little different. I write it like that. And I'm going to change this other f to a capital F. And actually, I'm going to make these all vectors. And I'm going to change them to d dt because that was the variable I was integrating over when I was doing my specific problem. Okay. And then what's little a equal to? Ti, and b would be tf. Okay. Okay. So that means that I can take this formula and I could say that my integral, I'm going to change my a and b to my ti and my tf, of f of t dt, which is, remember, what my impulse is, that I could write that as t final minus t initial times f average, right? Just doing a little cross multiplying, however you want to look at it. And I could rewrite this again as f average times delta t, because that's what tf minus ti is. And what that means is I can say that the area under the curve is equal to some average value of f times delta t. So my average value of f might be somewhere around here. Maybe a little lower. Okay. And then what I'm saying is the area here, which is this, is the same as the area here, which is that. And you might ask why I care. Well, sometimes, especially in physics, it's enough that I know what f average is. I don't need to know what happens to the f the entire time. I just need to know what the average value is, and that's enough for whatever I'm calculating. So, one of the hint, clues, as Mrs. Leas might say, is that if you're doing a problem and it talks about the average force, you need to use impulse and change in momentum. Okay, there will be various things, and we've already, I think, talked about at least one as we go through the year, where they're going to talk about something. Like if they talk about the rate at which the work is done, what does that mean? Power. Okay, so if average force comes into a problem, I am 99.9% confident that you're going to have to use impulse and momentum to solve the problem. So I just want to kind of write this out one more time, that impulse is equal to the change in momentum, and that's also going to be F average times delta t. Because that means that I can also say that F average is going to be delta P over delta T, which I may need later. No. Well, impulse is going to have the same units as what? No. Impulse is going to have the same units as, it is, but it's momentum. Well, power and momentum will never be in the same problem. I mean, in the same equation, I'm sorry. They may very well show up in the same problem, and you just have to use the context. Remember that power is a what, though? It's a scalar, okay? Momentum is a vector, all right? So that's a first indication. I tried to use for me, momentum is a lowercase p, unless I'm talking about the momentum of the whole system, in which I might use a capital P. So this would be the momentum of an individual object. Whereas capital P would be the momentum of the system. Well, the equal signs, they're in a different place. I mean, they are. If I draw, hang on, let's bring it up higher here. Okay, so we can talk about it. If I look at the line that I am writing on, those P's are in different places. And then P just by itself is power. So you just have to use the context. Okay. No. Nope. I want to do, what else do I want to do? I have one more problem I want to do, and then you can do the activity. All right, but I'm not going to introduce this whole concept, and then we're not going to practice it. All right, so let's do sample problem 19, please. If somebody would read it for us. Okay, so again, it's talking about average force. So, milliseconds. Ew. Well, how long do you think the ball and bat are going to be in contact with each other? You do not watch enough baseball. Well, it's 0.002 seconds because it's 2 milliseconds. Anything, any kind of object. Anyway. Okay, so initially the ball is moving this way at an angle of 35 degrees below the horizontal. It's a softball. Softballs make those arcs through the air, so it's coming down when it reaches the bat. And then afterwards, the batter hits the ball straight up so that the final momentum is completely vertical. And this whole interaction takes, like we've just bemoaned, 2.0 milliseconds, which is 2.0 times 10 to the seconds, yes. And like we've talked about, if it's asking you to find, especially the magnitude of the average force, then we're going to have to use impulse momentum. So remember that the magnitude of J then will be equal to the magnitude in the change of momentum, which will be equal to the magnitude of F average times delta T. So I have delta T. what else up here can I figure out? Well, the average force is what I'm looking for, but I need something to put on the other side of the equation. So what else can I figure out? It is, and more importantly, yes, it is. Okay, so I can figure out the change in momentum. That's probably what threw me off. That momentum is equal to mass times velocity. So remember, though, that momentum is a vector, as we just talked about. So that means that I have to take direction into consideration. Initially, the ball has momentum in what directions? Initially, y and what? X. Okay, if we assume a standard XY coordinate system. Okay, and afterward, what direction does the ball have momentum in? Positive y. Okay, so I'm going to have to treat the x and y directions separately and then combine them because I'm really looking for a magnitude. Is that right? Okay, so I think we'll just go to another page here. That didn't do what I wanted it to do. So here's my ball. Here's my PI. So I'm going to have a PIX and a PIY. And I know that angle is 35 degrees. And afterwards, I only have a PFY. Okay. Ow. So let's look at the x direction. So Jx, which is going to be delta Px, is going to be PFX minus PIX. So what's PFX? 0. What's PIX going to be? What's P? How do I find momentum? So it's going to be the magnitude of M times the magnitude of V. Oh, no. Well, we could do this. We could do that if you want to do that. That wasn't what I was going to do. I was going to make it PI cosine 35. It doesn't matter which way you do it. You can do it any way you want. So I was going to make this negative VI cosine 35. It's going to give you the same. It's just a matter of where you put the cosine. I like it when things make sense. So we can substitute in here. We've got negative, what was it, 3 kilograms? Was that right? And the velocity is 12 meters per second. Cosine 35. Make sure you're in degree mode in case you switch to, what's up, Sari? Yeah, I just like I had on the last screen. What? because that was the initial velocity of the ball. Nope, that's afterwards. I believe. I could be wrong, but... So negative 2.95. We'll keep an extra sig fig around because it's not a final answer. And what are my units going to be? Yeah. Nothing snazzy, doesn't have a fancy name. They ran out of dead scientists to name it after. Yes, it has to do with radiation. And usually you end up with millicuries, I believe, because I think a curie is a fairly large. I think you're kind of dead if you're talking about curies. Yeah. But it's a question of who did they name it after. If you want to get. But so did he. They worked together. I don't know that. I'm just saying it depends on who they named it after. They could have named it after both. But I don't really know. All right, so let's talk about the y direction. So I've got JY, changing my momentum in the y direction. So that's going to give me PFY minus PIY. So my PFY is pretty easy, right? Because what's it going to be? No. Yeah, MVF. Zoe, don't succumb to the sickness, okay, Zoe? I know, but don't succumb. Don't let it fog you up. All right, so let's be careful here. Because there's an algebraic negative sign. But there's also going to be a what negative sign? Because what direction is PIF in? Negative, because it's pointing down. All right? So it's going to be negative MVI sine 35 degrees, no matter how you want to cut it. So this is going to give me my 0.3 kilograms. Now pre-up, it's 10 meters per second for VF. Negative 0.30 kilograms, 12 meters per second, sine 35 degrees. And what do we get for JY? Okay, did other people get that? All right. Excellent. Okay. So what I really want to find is the magnitude of J. And how do I get the magnitude of J from Jx and Jy? The square root of the sum of the squares of the magnitudes of the squares. Okay, so that's going to tell us that the magnitude of J is going to be what? Yeah. Did you square everything? Okay. Okay. All right, Sarah, you with us? We're not to the final answer yet. You're absolutely correct. And when we get to the final answer, we'll do it. But we've still got one more calculation because what are we trying to find? F average. Okay. And remember that F average delta T is going to be the magnitude of J. So F average is going to be J divided by delta T, or 5.86 kilogram meters per second divided by 2 times 10 to the negative 3 seconds. And what do we get for F average? Okay, so let's make it 2 sig figs. Let's make it clear that it's 2 sig figs. So 2 point times and then what are the units going to be? They should be newtons. Are they really newtons? You better check. So what do you have up here? No, I can't cross out the seconds. So it really is a kilogram meter per second squared. Remember, units are a way of telling you that you did it right. You might lose the 1/2 or whatever constant might be in front, but the units have to work out. Nope. Because it's kilogram meters per second divided by seconds. So it's kilogram meters per second. If I'm dividing, that's the same thing as multiplying by the reciprocal, right? Okay. What do the freshmen say? Keep, change, flip or something? My son started to do it. I'm like, ah, that's where that comes from. All right. So I think we'll end it here for today.